Welcome back to Introduction to Probability and Statistics. This course is designed to give you a clear and practical understanding of the most important concepts in probability and statistics. So far, we have covered the basics of probability, random variables, how to find expected value of a random variable, and also discrete distributions, including Bernoulli and binomial distribution. In this lecture or video, we discuss some of the most important continuous distributions. Also, please note that the full lecture notes are available online. Just check the link in the description below. And if you like this course, like this video and subscribe to Dr. Data Science. So if you need to know only one distribution from the class of continuous probability distributions, that one is the normal or Gaussian distribution. It's a distribution that is characterized by its symmetric bell-shaped curve. And the probability density function, or PDF, for this distribution has this form, which we have 1 over the square root of 2 pi sigma squared. And then we have an exponential term, exponential of negative x minus mu squared over 2 sigma squared. And this random variable, as you can see, the PDF is defined from negative infinity to infinity, meaning that it can produce a real value number anywhere from negative infinity to infinity. So like the other distributions that we have seen, like Bernoulli, which had that parameter p, probability of success, here we also have parameters. There are two parameters, are mu and sigma. So mu can be just any real number from negative infinity to infinity, but sigma must be a positive real number. And right now, we don't know exactly the mean and variance or standard deviation of this distribution. However, very soon, we're going to show that the mean of this distribution is mu. So this distribution is always symmetric around its mean. And also the variance here is sigma squared, which means that the standard deviation is the square root of that, which is sigma. And we also usually use this notation n mu sigma squared, which means that the first entry is the mean, the second one is the variance. Here we have plots of the probability density function for different values of mu and sigma. So you can see that we set mu equals to 2. And when the standard deviation or sigma is smaller, like the blue one here, you can see that this distribution is more pointy, right? So it's kind of like, a sharp, increase at 2, which is the mean, and then it goes to 0 faster, compared to the other ones where you have higher standard deviations, because in those cases, the distribution becomes more, becomes flatter or more smooth. But in order to show that this mu and sigma square are indeed the mean and variance, there are multiple ways to do this. In one of the previous videos, we talk about moment generating functions, or MGFs. And then we talk about the fact that if you take the derivative of the moment generating function with respect to t, and if you do this once and set t equals 0, you get the mean. And if you do this 2 times and set the t equal to 0, then you get the second moment, which can be used to find the variance of this distribution. So here, the way we start is by the moment generating function of the normal distribution, which is the expected value of e to the power of tx, which has this formula, exponential of mu t plus 1 over 2 sigma squared t squared. So we can take the derivative of this, as you can see here. We get this exponential function times mu plus sigma squared t. And if we set t equals 0, we just get mu, which is the mean of this distribution. Now, in order to find the variance of this distribution, we can find the second moment, aka e to the x squared, e of x squared, or expected value of x squared. And in this case, in order to find this, we have to take the second derivative of the moment generating function and set that equal to 0. So in what we have here in the first line, we set t equals 0. And in this case, you see that we end up with mu squared from the first term and then sigma squared from the second term. Therefore, the second moment of this normal random variable is mu squared plus sigma squared. And the variance is calculated as the second moment minus first moment or mean squared, which this gives us sigma squared. And this completes the fact that mu and sigma are indeed the mean and standard deviation of n, mu, and sigma squared, as we just mentioned earlier on. Normal distribution is very important. Therefore, we have a subset of these, which is called the standard normal distribution. A standard normal distribution, which we usually show this using the variable z, uppercase z, because this is a random variable. It's simply normal distribution with mean 0 and variance 1. And that's what we call it as the standard normal distribution. And the reason this is very important because what we really want to know is the area under the PDF of the normal distribution. And one way to look at this is what we call it as Z alpha, right? So Z alpha, what this is relates to the idea of cumulative distribution function that we have. So we want to find probability that Z, the random variable Z, greater than or equal to Z alpha equals alpha. So we want to know what Z alpha is. And this means that if I just go to the next slide for a second, so this means that if this is the standard normal distribution, the PDF of a standard normal distribution, and let's say I want to find the, for alpha equals 0.025, a point on the x-axis such that the area to the right of that, right? So this is what we call as the tail probability, is 0.025. So what that point should be, and if you use Python, or you can also use something called Z-table that we used before having access to scientific computing libraries, you can see that that point is 1.96, right? So again, since this is the standard normal distribution, if I look at x equals 0, I know that I have 0.5 area to the right, 0.5 to the left, right? So that's what we know based on the symmetrical properties of normal distribution. But we know that as we move to the right, the area to the right, or that right tail, becomes smaller and smaller. But at one point, at which point we get to these 0.025, and that's at Z alpha, which is 1.96. So that's the basic idea here of this Z alpha. So it tells us at what point we are going to have alpha area to the right. And this is what is also sometimes known as the Z score, which relates to the area of the standard normal curve to its right. And using the properties of probability, and in this case the complement rule, this means that at that point Z alpha, the area to the left, right? So that's the probability of Z less than or equal to Z alpha, is equal to 1 minus alpha. So in most libraries, especially in Python and using SciPy, which is a very useful package or library for statistical and probabilistic techniques, we can use something called percent point function, or PPF, which is the inverse of cumulative distribution function, right? Because that's exactly what we are really doing here, right? So instead of finding probability of Z less than or equal to whatever number we give, we want to know what the probability should be, and we are trying to solve now the inverse problem, that at what point we get certain probability to the right and to the left. And as I said here, you can use this in SciPy, in the stats module. You can use norm.ppf, which stands for percent point function. And this is the visualization again, that we have this Z alpha, which is 1.96, and using the symmetrical properties of the normal distribution, so the area to the left of negative 1.96. So if I just find or use the symmetry around this Z or X equals to 0, then the area on the left tail is also 0.025. So this kind of summarizes this, right? That if I choose 1.96 on the x-axis, then I have 0.025 area on the right, and then to the left of negative 1.96, I also have 0.025. So if I add this together, I get 0.05, which means that in the middle or the central part, I have 1 minus 0.05, which is 0.95. So this is one of the most important concepts when you're working with the normal distribution, to find this central area. And the way we do this, because we have access to the z-scores, is by understanding how much area we have to set apart from the tails. So now we know how much we have in the middle. And we use this using the complement rule that we discussed earlier on. So it means that in general, in this case, we can show that the probability that the random variable z, and this is the standard normal, between negative 1.96 and 1.96 is exactly 0.95, or that's a central 95% area. So now you may ask that, well, in general, I may not have a standard normal distribution. Then what? So we can actually convert any normal distribution to the standard normal distribution by using a very simple transformation. You find the mean or mu, the standard deviation sigma, and then you form this x minus mu over sigma. And the reason I call this z is because this transform random variable has mean 0 and variance 1. It's very easy to find this using the properties of expected value we discussed before. So E of, or expected value of z, is expected value of x minus mu over sigma. And if I use the linearity of expectation, we see that the numerator is 0. And the same thing with the variance, right? Again, here I can write this expected value of x minus mu sigma, the whole thing is squared, as sigma squared in the denominator, right? Because that's, what we get as the scaling factor. And in the numerator, we have x minus mu squared, and the expected value of that is sigma squared. So this shows that any normal random variable with mean mu and a standard deviation sigma can be transformed to the standard normal random variable. Which means that, so now if we put these two pieces together, right, to identify this 1 minus alpha area of the normal distribution with alpha over 2 in each tail, right? So if I have alpha over 2 in each red tail that we have here, then we end up with 1 minus alpha in the green central area. And we have to use this critical value z alpha over 2 to figure out where those points are. For example, we know that for 0.025, that's 1.96, etc. There's a table, or we use SciPy to find that. And this gives us this probability that z between these two critical values is equal to 1 minus alpha. And given the fact that we know that z is related to the original random variable via this transformation, x minus mu over sigma, now we can plug in this into that probabilistic argument and then multiply both sides by sigma and then take mu to right and left. So that's exactly what's happening, right? So we get that x is between mu minus z alpha over 2 times sigma and z alpha 2 plus times sigma. So we have this plus minus z alpha over 2 times sigma. And if you're interested in, again, like alpha equals 0.05, then it means that we're looking at z of this number divided by 2, because we have 2 tails, and that number is 1.96. So the probability that a normal random variable is between mean minus 1.96, or let's just approximate as this as 2. So the probability that this random variable takes on values from the mean minus 2 sigma to mean plus 2 sigma, and sigma is the standard deviation, is 95%. You can also calculate this for different numbers. Like, what if I want to set alpha equals 0.32, which means that I have 0.16 area in each tail? Then you can see that in this case, the probability that the normal random variable is in the interval of mean minus sigma to mean plus sigma is 0.68. And to recap this means that when we work with normal distributions with any mean and variance, 68% of total probability lies within one standard deviation of the mean, and 95% within 2 standard deviations of the mean. Okay, so this is an extremely important sort of like rule of thumb to remember, that with normal distributions, obviously because they have like the most of their mass kind of like center around the mean, so obviously, you know, as we get further from the mean, we are going to have more and more probability or area under the curve, and 68% within plus minus standard deviation, and 95% within plus minus 2 standard deviations. So this concludes our discussion about normal distribution, but normal distribution also has a lot of applications for or other extensions. And one of them is the chi-square distribution, which is the sum of the squares of k independent standard normal random variables. So in this case, as you can see, if I have k standard normal random variables that are independent, and I square them and add them together, I get this chi-square distribution, and we have something called the degrees of freedom, right? So the degrees of freedom here is actually k. So you can see that for k equals 2, 3, and 5, how the PDF looks like. So this gives us a lot more flexibility, especially in terms of modeling random variables that they don't have that symmetrical bell-shaped curve that we had with the normal distribution. And then the final distribution it would be nice to introduce here is the t-distribution. And remember, if in this case we have 2 random variables z and chi-squared with k degrees of freedom, the 2 distributions that we already discussed, now if we divide the standard normal random variable z by a square root of chi-squared over k, the resulting random variable, which we show that using tk, is t-distribution with k degrees of freedom. And so the shape of this distribution is really determined by the degrees of freedom. And as k increases these degrees of freedom, then the t-distribution approaches the standard normal distribution. And for a small case, the t-distribution has heavier tails, which if I want to show this, right? So in this case, you can see that we have the dotted curve. That's for the standard normal distribution, mean 0, variance 1. And you can see that t-distribution, for example, here with degree of freedom 1, has this heavier tail. So you can see that the area under the tails, right and left, are greater than the cases, for example, we have a standard or t-distribution with degree 5 or 10. So that's something important to remember, that if you want to have heavier tails, meaning more area or mass under that, under those tails, then we can use something like a t-distribution. But still, we have the symmetrical probability distribution here. And then the final thing is the normal approximation to binomial distribution. Previous lecture, we talked about discrete distributions, and in particular binomial. And we saw that before, that it looks like, right, this was a case where the number of trials or experiments was 20, and then the probability of success was 10. That even though this is discrete, right, because you can see these bars here, so this is a discrete distribution, but it looks like a normal distribution fits this very well, right? And therefore, that's like a general rule of thumb, that when you have binomial distribution, even though it's a discrete distribution, it can be approximated by a normal distribution. And usually this is the case where that n times p, and p is the probability of success that we discussed, and n times 1 minus p, they're greater than or equal to some number like 5 or 10. So you have certain, assumptions to make sure this is a good approximation. But you can see in this case with n equals 20, p equals 0.5, we have a normal distribution that actually the mean is n times p, as we know, and the variance is n times p times 1 minus p, and you can verify that here. So why is this an important approximation? So let's say you have a production line or production process that has 5% defect rate, right? So think about it as like Bernoulli or extension of this to binomial, where the defect rate is 5%. You produce 500 items, so that's when we go from a single experiment to 500 experiments. And x here is the total number of defective items. And we want to find the probability that x is less than or equal to 30. So you can try to solve this problem directly using binomial distributions probability mass function, but that can be very difficult because you have to find some n choose k or n choose x that we had before. So instead of doing this, you can use the normal approximation, right? So x is binomial with n equals 500 and p equals 0.05. So this means that the mean and variance, we can find them, n times p1 minus p. And you can see that in this case, if we use a normal approximation, right? So we want to find probability of x less than or equal to 30. Now we can assume that there is this, normal random variable y with mean mu and variance sigma squared, which we found them. And in this case, if you want to find this, you can use the idea of, z-score that we discussed, right? Or the CDF of a normal distribution. So you're going to subtract both sides by 25 and then divide by the standard deviation. So therefore z now is the standard normal. And whatever we have on the right-hand side, we can find that is about 1.03, and you can use SciPy or a z-table and see, what's the CDF of a standard normal distribution when the input is 1.03, and that's 0.85. So this means that in this case, we don't have to go through the binomials probability mass function because it's more complex to use that. And we found that the probability that we have less than or equal to 30 defective items is actually pretty high. It's about 85%.